Good afternoon. You've nearly made it. One more talk to go. I try to keep it entertaining. So this is kind of like part 3 of a sort of trilogy of Swift-related talks at BobConf. So 2 years ago, I talked about how good Swift is for functional programming, as a language for functional programming. And last year, it was about bulk data structures and how Swift allows you to maintain them as immutable data structures, which is super important for functional programming. And yeah, today we're going to look at user interfaces. So user interface development is actually quite hard. Who has written kind of really UI code, hardcore UI code? OK, so maybe you agree with me, maybe not. But well, you have to deal with concurrency. There are like events happening, and you have to send, if you have a phone app, it has to be responsive. So you have to send stuff on to background threads to do stuff. Testing is difficult because, well, user interaction, graphics, and many interlinked responsibilities. The APIs of professional UI kits are gigantic. It's basically impossible to ever know the whole thing. And well, and you need to know something about design or have a designer, and then you have to kind of structure this communication. But the worst thing is state. You have your state, and you have stuff on the screen, and it kind of half of the time doesn't fit together. And state, well, if we say state, then the next reaction should be functional programming can help us with that. So let's see. And to make it a little bit more tangible, I've got an example app, which I use as a running example. So imagine New Year's Eve, actually the morning after, you're totally hangover. You're kind of like, I have to improve my life. And then you come up with all those promises. I'll be more fit. I'll do more sports. I'll go outside, away from my computer more. So here's a little app to help you with that. There are like 2 screens in a tab view. And then on the right one, you can dig down. And to see how that works, a little demo. So here's the app. You can switch between the 2 screens. And then on the left screen, you have an overview, and you can advance. If you did another walk, you can advance that here. In the right one, you can dig down, look, edit your list of goals. You can change properties like the color of one of these types of goals, and that's then, of course, reflected in the other one. And you can change the intervals. You can have modal dialogues. And you can change intervals. And again, if you say, OK, I want to do 2 more walks per week, then that's reflected automatically in the user interface. That's what we expect. So what's the underlying data for this? Well, in Swift, we define a struct. A struct is like a Haskell record. It's a product type with labels, with all these properties. And then we pair these goals with progress. Now, this question mark thing is an optional in Swift, so maybe type in Haskell, which means if there's no progress, it's not active, won't be shown in the summary screen. And if there's a number, well, that's how often you have performed it. And then at the end, we'll chuck multiple of these goal progress records into a list on array, and wrap that in a class. So this is like your typical Haskell program with an I/O ref of a list of things on the top level, because, well, that's your state for interaction. Well, now the whole question now is, how do we get these 2 things together, right? And that's where things get complicated. I mean, this is a simple app. But imagine this in IDE, like a million different views and a complicated data model. And when something changes in the data, we have to have some dependencies to know what we have to update. And we only want to do the minimal redrawing because, well, have your multimedia app with lots of data and you want to quickly scroll through it, if you redraw too much, it'll be horrible, unusable. And then we need also local state, which is not reflected in the model. Like we had this model dialect, the alert box. Yeah, there's something locally happening that has nothing to do with the model, right? And we want to keep the whole thing nice and modular. And having all of that at the same time, that's the hard part. But SwiftUI to the rescue. It's a I want to convince you, by way of the rest of the talk, that it's a declarative modular framework. One way it achieves this, it separates layout from content. So it's a bit like LaTeX. You have styles, and you have the content, or like CSS, kind of separation. But in many GUI toolkits, it's kind of mixed together. And the whole description of the views goes with an embedded language. So you really describe what should be visible on the screen, and how that's put on the screen, that's SwiftUI's problem. So in that sense, it's declarative. You describe what you want, but not how that's realized. And it's cross-platform. I'll say more about that later. And quite scalable. You can write big desktop apps with it and not just little tooly thingies. OK. Now, before we look at how SwiftUI achieves that, let's take a step back and talk a little bit about principles of architectures for user interfaces. So there's this zoo of architectural patterns. Model view controller, model view update, model view presenter, model view adapter, model view model, model view model with a coordinator. And at that point, they got fed up. And next one was Viper. OK. We don't want to discuss all them. But we look at model view controller, the kind of extreme object-oriented architecture, and model view update, which is kind of the functional opposite. And everybody knows model view controller. I mean, this is really the old architecture which was introduced in Smalltalk in the late 70s. But Apple's frameworks, the Cocoa frameworks, they're also based around this. I mean, a lot of Apple stuff, if you know Apple stuff, is based on Smalltalk things, including Objective-C, which is now gone. Anyway, in model view controller, you wouldn't have guessed it. There's a model in the view, but also controller. And the controller is kind of coordinating all this. There usually, in the original model, there's direct data flow between model and view. But the controller could rearrange, reconfigure views. And if there are like validation of data, it would do that before putting model. Sometimes people recommend to kind of do everything through the controller, yeah, and then you get this through. Now, that's the theory. It looks nice with these three kind of entities, as if there are only three objects. But in reality, that's not the case. We have a lot of view with a lot of view models, view objects. And in the model, we also have a lot of classes, usually, with a lot of different objects, and then controller objects to manage them all. So in the kind of like, let's use an AI tool, in our talk, I thought, well, let's ask one of these tools, how could I visualize something like that, actually how it really looks like, not just three objects. And because we care about digital sovereignty, as we discussed this morning, I used the European tool, and it came up with this. And I think that pretty much captures this. You have this large object graph and lots of explicit dependencies which you have to match. And there are imperative updates happening through this all. And because this is too complex, at least on Apple platforms, what people do, they stuff everything into the controller, and then you get some untestable big mega objects. So can't we do this in a more functional way? Welcome to Model View Update. Well, in its purest form, I think We find this in Elm, the kind of Haskell variant for web programming. Yeah, so of course, model and view again, but in Elm, there's one function which takes the model, the whole thing, and produces the view. And if you have a new model, you get a new view. Simple, but very monolithic. And the other way around, I mean, if you click on something, then the view sends a message, and there's an update function which takes the model, gives you a new model, and maybe a command to do some external I/O or whatever. So very simple, doesn't scale very well, not modular at all. So Facebook came up with this internally Flux, externally React Redux combination with a similar approach, but in a way that's more scalable, but also a lot more complex than in R. Now, if you want to know more about this, I can recommend this paper by Mike and Marcus, which partially actually inspired me to give this talk here, because they identify 3 challenges for these kind of user interface architectures. One they call the update challenge, and that is in the MVC approach, you kind of write the code to create views twice. You write the actual initial view creation and then update code when things change to in place kind of manipulate the existing structure you've got. And that is very similar to the initial code, but not really the same. So you have 2 versions. So MVC is not good at this. But then modularity, we talked about how Elm puts everything in 2 functions, which are global, nice, simple, but modularity goes totally out of the window. And circularity is, again, something MVC struggles with, because in more complex interfaces, maybe network packet comes in from your cloud, whatever thing, that updated something in your view, which updates in the model again, which updates the view, and then chaos. So I actually want to add 2 more, namely, doing this well is not only isn't enough. You actually have to really care about performance for bigger apps, for multimedia apps. Minimizing updates, super important. And extensibility, because not only are these frameworks gigantic, they are also too small. You regularly run into situations where you need new widgets, new graphical things, and you need to be able to create them yourselves. This can't be something which is just kind of, here are your Lego bricks, and you can't have any more. OK, so let's look at SwiftUI and kind of then relate it to what we talked about, the frameworks. Who speaks Swift? OK, so a protocol in Swift is a type class in Haskell. OK, so this is view protocol is a type class. It's the type class of all things you can show on the screen, kind of, or use to produce views. So a very simple one is the text view. You give it a string, and, well, you can imagine what it does. Views can be annotated by modifiers. Modifiers are just functions from views to views. So this thing takes this text view and just uses a different font for the text. All right. So now you can define your own views, which you define as structures. And structures in Swift, I already said, they're immutable value types. They're not like classes, or they're really like a data structure in Haskell. And now it becomes a bit confusing, because this is a bit Swift idiomatic. We have a body variable, which actually is not a variable. This is just a shorthand for a function with no arguments. Okay, it could be func, brackets, arrow, but, well, this is shorter to write. So this is called the body property, and the protocol, so the type class, requires all view structs to have this thing. This is like one of the methods of the type class. Okay, and then in that function, you write your view code. So that's the function you call to create the view. All right. So now that we know the basics, let's go to our example and try to build it. So just like before, we have a new view struct, only this time around, it gets an argument, the model we are trying to put on the screen. And then there's a VStack. A VStack is a vertical stack of things. Well, that fits here. And then the first thing in the stack is this whole grid. The second thing in the stack is a spacer, which pushes the text and the grid apart. And then we have the text, which we already seen. And finally, we have a view modifier for the VStack to put a little bit of spacing on the top and bottom. OK? Easy. That's a declarative way to describe this UI. Now, the grid itself, same thing. View struct gets an argument, has a body property. But now for a lazy vertical grid. So looks like a grid here. Some parameters to fix the visuals. And then there's a for each. For each is basically a map over views. So this for each iterates over the goals in our model, but we filter out all the goals which are not active. And then this is syntax for lambda. So that's the bound variable. And behind the in is the body of the lambda. And so that means for every goal, we produce a progress view, one of these little round things. And the progress views, they actually get another argument. And the curly braces here are basically a way to say, well, make this a lazy argument. We only call this when we need to. And that's the thunk which will be evaluated if you tap on one of those, because they're internally a button. So in that way, we have described this quite a bit more complex structure. All right. That's the basic way to construct the view. But we said we also need local state because of modal views. But also, sometimes you enter stuff, and it needs to be committed. And while it's not yet committed, well, it's local. It's not yet in the model. For something like text editor, you have an undo, redo, queue. It's also something which is usually not persisted. So all this stuff has to be kept local. So how can we do that? Well, let's look at the example of modal views, because that occurred in our example app. Here, when I clicked on this, I get this alert, which I can cancel or say I want to delete the progress. So that's a local, the thing must know the alert is visible now. So to do that, we introduce something new, state for local state variables. In this case, just a bool. If it's false, the alert is not shown. If it's true, the alert is visible on the screen. I elided the code which sets this to true, because keeping it on one slide. Important thing is this. This, again, a view modifier. It doesn't change the styling. What it does, it takes this view, the form, and adds a potential alert box. Now, that alert box is presented if this local state deleting progress is true. So just by flipping this bool, the dialog will be shown or not. In fact, it will be animated in and animated out when this thing flips. That's what I mean by declarative description of the view. We describe what we want the thing to look like. We don't have any code which creates the alert, shows it, removes it again. That's all done by SwiftUI behind the scenes. And then we can configure the alert. It has some buttons. In our case, it had 2. And then there's a message to it. Again, this just says what ought to be on the screen. SwiftUI's problem to render it, realize it. Now, I forgot one thing here. This dollar, nobody asked, confusing, why a dollar? Well, this means we want, this is a binding, which means we want to basically this as a lens, kind of a lens in Haskell. So bindings are kind of SwiftUI for a restricted form of lenses. And to see how this works, we'll have a look at this toggle here in this dialog. So here we have a binding, again, of a bool. It's a different one than the one before. And then in the body we use this with this toggle. And when the user, it's not easily visible here, there's this toggle still here. If the user changes this toggle, that will flip that bool. And this lens, the binding lens, can point to a subpart of the app state of the model or local state, depending on what you need. And in this way, connect the two in this lens setup. OK, and that's actually all the basics for SwiftUI. It's actually conceptually a very simple framework. So you could argue that it combines the best of both worlds. So we have kind of a view function, but not one view function, but all the body properties taken together give us the overall view function, and it's nicely chopped up modular per view. And the update function is a combination of bindings, so this lens slice type way of kind of getting at bits of the overall model state, and event handlers, which, like you saw with the buttons, where the kind of thunk, lazy thunk on the circles, which you could tap, is kind of like an event handler setup. And then we have local state, which can be used via bindings to realize complex local state situations. OK. So it feels a bit like magic, maybe. To me, it always feels like, oh, OK. So how does this work? How do we get from this declarative description of I want this on the screen to efficient selective screen updates, which work in situations of a complex interface in a multimedia application that really has to handle a lot of data? Well, the basic idea is actually quite simple. And if you know React, I mean, it's, of course, a very related idea. So we'll take this example again, like the progress view of the little app. And that code basically builds this tree. We have the V-stack with the 3 things, and then the scroll V. In the scroll view, we have a lazy grid, and that has this map over the views and all the little circles underneath. So that's called a view tree. Not very surprising, because these are views. Now, the view tree is not the object structure for the user interface. It's more like a blueprint of it. It is what Swift, it's like the CML spec for Alex's Claude instances. It describes what I want to have, but it's not the thing. That SwiftUI has to figure that out. And they're cheap. They're just, I mean, it's just an algebraic data structure. You can quickly build relatively big ones, and that can happen many times per second. So that's a cheap thing. And then SwiftUI diffs those between updates to figure out what changed in the user interface. All right, so that's the blueprint for the interface objects. So where is the actual user interface? Well, that is called the attribute graph. And that consists out of a few things. And this is all hidden. So the developer using SwiftUI can't even touch that. That's internal to the framework. So they're the actual views for iOS, which was in our example. These are UI views. For macOS, it would be NS views. For something else, it would be even some. That's the native objects actually representing the view objects on the screen. Then there are state objects, like the bool we had, which toggled the alert being there or not. And then there are observation dependencies, which I'll come to in the next slide. Now, this is the attribute graph. That's what persists between updates and update cycles, and which, by diffing, SwiftUI determines what to statefully update in place to achieve the effects, including animations. So if you toggle this switch and the alert pops up, then there's a whole animation sequence which SwiftUI pre-generates and then rolls out over time in order to implement one flip of this spool. So what remains is, what's this observation stuff about? Well, the observation framework is something which I kind of left off in the initial slide when we had the model. There was one declaration missing, not to describe the actual data, but for SwiftUI. So this observable is a macro. SwiftUI has a macro system which is quite similar to template Haskell. It's, you could say, a disciplined version of template Haskell. So how is it disciplined? Well, for example, you can actually cross-compile programs with it, which reacl-c doesn't probably manage to this day. But also in other ways, it's a bit more structured, a bit more restricted also, but it still covers most of the applications you would use template Haskell for. And this is a macro which takes that class definition and kind of rewrites it into an observable version of the class. And that also works for larger classes, of course, and classes within classes and whatever you want to do. And what it basically adds are hooks such that it can dependency tracking whenever one of these body properties of the views is executed, then the observable kind of rewrite makes sure it tracks in this particular execution of the body property, meaning if there are conditionals in there, it takes actually only into account what is actually executed, not what's statically in there. So what's actually used tracks which components of the model are used for this particular execution of this body property of this view. And then when it does, so this, I call this kind of dynamic dependency tracking, because it changes also from view update to view update what the dependencies are. And then when it comes time to do the diffing of one view tree and the next iteration of the view tree, it looks at which of these things, which of these views have changed, run the body property, do the dependency tracking, and if any of the dependencies changed, then all views which depended on this dependency also need to rerun their body properties, and so on. And in that way, really the minimal amount of views is redrawn. So it's kind of observer pattern, but fully automated, and you don't see it. And it's also something actually the developer doesn't have to care about, because the previous version of SwiftUI actually used a framework called Compose, which is like Swift's or Apple's functional reactive programming kind of framework, instead of that. That was a little bit less magic-y than observation, but observation, yeah, really completely works behind the scenes. All right, so that's basically the fundamental way in which it works. So let's take a step back. Looks cool, I guess, but yeah, how does it, what can you do with it? Well, you can do a lot. This is the app I'm currently working on. It's an IDE for functional languages, and it's all written SwiftUI. So this is what I would call a complex user interface, and that's absolutely doable. And I said SwiftUI is cross-platform. Well, in two ways. On one hand, inside the Apple ecosystem, this is about basically the size of the interfaces cross-platform. You can actually write watch applications with it and Apple TV applications with it and macOS. And having one toolkit for these very UI type-wise, very different devices is a challenge. And in the previous UI frameworks of Apple, this was absolutely not possible. You had like 3.5 different ones. But it's also cross-platform outside of the Apple ecosystem. So there is a project called Skip, which is basically SwiftUI cross-platform for Android and iPhones. And that's a quite mature project, which you can use in production, people use in production. And then the second one, Swift Cross UI. Yeah, sorry it's difficult to read down there. So Swift Cross UI actually covers also Linux and Windows. That's a more kind of in-development project. Also, of course, a lot harder. If you restrict yourself to 2 phones, then, I mean, there's a lot less variation, of course. But yeah, I mean, SwiftUI is really moving outside of the Apple ecosystem. And especially for this use case, I think that's what a lot of companies actually struggle with. And then if you are like coming from a web world and you really like this React Redux combination, well, there's an answer for you too, actually 2. There is something called the composable architecture, which is actually goes beyond Redux. It's a very elaborate compositional state management system of, there are 2 guys, they make videos and learning material for software development. They're called Point Free, and they're like one of these super functional programming evangelizing for Apple developers kind of outlets. So they have really good stuff. And a lot of really good projects, actually, like open source packages. And then there's the immutable data framework, which is really much more focused really on the Redux for SwiftUI use case. And then coming back to, I said, well, beyond the 3 challenges outlined by in Mike's paper, I think extensibility and performance, performance kind of the scaling. But for extensibility, so for my IDE, I actually have a SwiftUI view, one of these structs, which implements a code editor. And well, that implements a new view, and it's a rather complex one, and it has a lot of local state. It ties into a lot of existing infrastructure in iOS and macOS, and this is absolutely doable in SwiftUI and well supported. So I think the extensibility is also covered. That's also open source, so if you need an editor component in your new app, then you know where to look. If you're interested to see the details, this example project which I showed you is on GitHub. And if you're interested in what I'm working on, then you can be one of my beta testers. So thank you very much.
And we have time for questions. Yeah.
So it's useful to give for Haskell developers who might be forced to write apps as translation dictionary. So I found it very helpful.
Thank you. Also, sorry to interrupt you, but my talk 2 years ago, where I explained how to do functional programming in Swift or how to translate Apple's terminology to standard functional programming terminology. Basically, for all examples, I have the corresponding Haskell code there. Okay. So that's a good kind of translation. Okay. Yeah.
So I was reading the views, the protocols are like type classes, and then our structs are like objects, data structures.
No, they're like a constructor declaration in algebraic data type.
Okay, yeah.
So they're like one of the alternatives in a data declaration.
So that's a data declaration, and the colon say is the protocol you were saying is like a type class?
Protocol is a type class, exactly. So it's just different syntax. So in Swift you write type colon protocol, and in Haskell you write type class, type as an argument, but it means the same thing.
Okay. And then the syntax of the at is it's a macro for the observable, and then you have the binding group and the state. Are those also macros, or are they, that's just this overloaded syntax?
Yes and no. They're so-called property wrappers. Property wrappers were introduced into Swift before macros. So originally we had property wrappers, and there are all kinds of property wrappers, not just binding. Also for other use cases, not just for SwiftUI. It's a general mechanism in the language. And then when they introduced macros, property wrappers became kind of one flavor of macros, basically. Yeah.
There was another question?
Yeah, thanks, Manuel. I'm just curious, what can be rendered in practice when basic say, please render this? Can this also be parameterized behaviors in the sense that it could be parameterized by like functions of time, direction, and I don't know, acceleration, so that when you render it, actually you see a movie and you turn the camera and you see basically what you write down is the function. And then what gets rendered then is actually depending on just like interactive programming. Can you express it the same way? Because it seems like the framework definitely supports that. It's by specifying what gets rendered is a function, and then actually what you see depends on actually how much time whatever has passed and so on. Is that possible?
So the internals, they are totally hidden. So this whole attribute graph and so on, you can't get at that. But there is an animation subframework. So I only showed you animations which happen automatically. You do an alert and it pops up, and but there was actually one when you tap on one of those, the ring kind of moves slowly. So that's actually animation. I didn't show you the code for this thing, but that's an animation I explicitly put in there. And there's kind of a 3-layered animation system. The simplest one is you just say, I want this change of this local variable, for example, local state, animated. And then depending on the type and the type of views, there's some standard animations, and there are some ways with view modifiers to change, like how quickly it starts, how long it takes, and so on. But then there are 2 other animation systems, and the most complex one gives you can really kind of define functions over the change of, for example, floating point variable, and you can define your own curves of how the variable should change and how that affects the view presentation. And in this way you can do rather complex animations just by basically doing what you described. So it's not kind of by hooking into the view function itself, but it's by in this animation subsystem, which is kind of a configuration mechanism for this view mechanism. Yeah. So partially. It's a short answer. Yeah, Mike?
So just to clarify, so if you were imagine an application that had UI components that were written independently,
Yeah.
Is it the case that each component needs one of those observable var things?
I don't quite understand. So
the point, if you have a component that is, let's imagine your goals app just becomes a component in your larger fitness tracker app, right? Then you could imagine from just a purely application standpoint that there would only be a single reference at the top level of your fitness tracker, right?
Yeah.
But then, unfortunately, so it seems to be the case that now your goal indicators, which are written as an independent component, right? When that thing wants to modify its own state from the view because somebody tweaks something, you need a var in that component, right?
That depends. So so you don't have to var everything.
No, that's why I said you need at least one var per component, right?
you need one var for the application. At the very top level,
Yeah, but then the problem is if you have a subcomponent, in order for the subcomponent to influence the overall state, it needs to influence the state of the surrounding application.
Not always. So, I mean, I didn't show you everything, of course. So, what you may have seen in the definition of the goal itself, the first property actually was ID. And there was actually another type class, identifiable, which requires this ID property. And so what a totally common pattern is for structs, which you want to be able to talk about, so get an identifier, you give them that ID, and it just uses kind of a UUID for those. And then a lot of the identifying which things you want to change, but also more importantly in lists and grids and so on, things you want to animate, things if you out of a list you select 5 things, you throw them away, you need an animation to kind of show that. All this doesn't work if you just use indices for these collections, but they have to have stable identifiers. Yeah. So you use this identity system to identify sub-components of the overall state, which you don't want to have to an explicit var to. So it's really more a question of domain modeling, where, I mean, if for the array, for the overall array, if I change one element, I said it's an immutable array. So there needs to be a new array and needs to be copied over, depending on how it's used. And that can be expensive. So for some things, like the file management here in this one, if I just plug this into one big array and try to, that's just going to be inefficient.
I mean, that's similar to the way that you need to label things in React, for example, so that it won't recreate the whole structure. But the point is, if the component, if there's a user interaction on your component, on your subcomponent, that affects the state, right? Somebody tweaks one of those fitness goals and says it's now at 74 instead of 73%, right? How does it notify? I mean, how does it make known that the state has changed? And I think the answer was it assigns to that top-level state variable the component, right?
Well, in this case, it was of the top-level class that actually has methods as well, and it was work.
Yeah, but ultimately, I mean, you needed to make it observable, so the notification goes through that, right?
But it doesn't have to be a var. I mean, I'm just saying I could have done something different. I could have made all these goals classes too, and then I could have passed. I mean, this would have been a very bad
offline.
Yeah.
Yeah, thank you.
Thanks.
Short question would be possible.
Yeah.
I had a question about the observable, because you only annotated on the model, like the top level. Does the macro just like propagate it down to every single sub? Or do you have
macros, if you put them on one class, it's on this class. So that's something where you have to pay a little attention. If you have in this class, I only had used other structs. Right. But I could use other classes. That really depends on what you need in your data model. And if that's the case, and they also need to be observable, then those class declarations also need an explicit observable. It doesn't automatically kind of propagate through the tree. And if you forget that, then some updates may be missing also. So easy fix.
it's probably hard to debug.
It's something where you can make a mistake. Yeah, absolutely.
Great. Thank you again.
Thank you very much.